The next speaker is Trevor Goodspeed. He's come all the way from Tennessee to tell you how to, well, manipulate medical devices. Well, you're not supposed to do that, of course. But despite the somewhat daunting title, I think we're going to learn quite a bit about microcontrollers that are used in, for example, medical equipment. And don't be shy because of the part 2. Part 1 was given at the Black Hat conference, but I think whoever missed out part 1 won't regret it. So let's first thank Trevor for coming over.
Howdy. My name is Travis Good. Can we turn that down just a bit? Hello? Okay, that's better. So in part 1, I described a theoretical attack against the MSP430 microcontroller, which is a 16-bit chip with a computer contained entirely within it. You give it stable power, and you can put a program into the chip, and it runs it, just as a larger computer would, except that it's embedded. You can throw it on a board and such. Since then, I've actually gotten it to work in hardware. I've broken a chip with it, and I've built this little device for attacking the chip. Some versions are vulnerable, some versions aren't. The basis of the attack, though, is in the timing of a password comparison. If you look at this waveform on the title slide, the left is an acknowledgement telling the attacker that it's okay to transmit. Between the two signals, the attacker is giving a password guess, and he's doing it with non-standard serial timing. Then the right waveform is the victim telling the attacker that the password is wrong, and that he's not going to be given access to protected memory. By using non-standard timing, then you can make it such that the only thing affecting the difference between these two waveforms, that's like the end of the first and the beginning of the second, is how correct the password guess is. And you can make this distance vary by 2 clock cycles per correct byte of your guess. So if you guess all zeros, and it happens, say, 6 clock cycles faster than an impossible password would be, then you know that the byte 0 occurs 3 times within the password. So you can run through all of the bytes, you can figure out how many times they each occur, and then you can go back and you then have the alphabet of the password. So you'll then have 32 or fewer potential letters to try, and then you just rotate them through until you get the entire thing. So I'm from Knoxville, Tennessee. It's a neighborly town. I'll soon be moving to Philadelphia, which is not quite so neighborly. I authored the first Stack Overflow for the MSP430. I maintain the reverse engineering tool MSP430 Static, which is the only presently maintained tool for taking apart this firmware for this chip. I reverse engineered the EZ430 in-circuit debugger, which I'll be giving a lecture on in 2 days, a traffic light controller, and the bootstrap loader, of which we'll be speaking. And lately I've been experimenting with voltage glitching and non-cryptography related power analysis, some of which you'll see at the end of these slides. The device that I'll be discussing cracks MSP430 bootstrap loader passwords only on vulnerable versions, which are those beneath 1.6 and above 2.01. So the older chips and then the brand new ones. For example, the 4618 and the 1101A are both vulnerable. The 4618 is like a top-of-the-line chip with more than 16 bits of memory space. It has an LCD controller, tons of I/O. The 1101A is a modern remake of one of their original chips. And this vulnerability was first disclosed at Black Hat USA. So this is an example board that we might be attacking. We've got a 4618 there in the middle and to the left of the board. It controls the LCD at the top. There's a serial port and some analog chains and that sort of stuff. Usually when you program this board, you use JTAG or SPI-by-wire. And in the case of JTAG, you connect to the board, and there's a physical fuse that can lock you out. If you're not locked out, you have complete control of memory. You can debug the device. You can single-step it. You can read from memory, write from memory. And there's no concept of a password. But this is all implemented in hardware. You have an actual state machine. You shift into registers and you shift out of registers. And there's no software implementing this within the chip. An alternative is to use a bootstrap loader. It's only intended for programming, not for debugging. The closest it has to debugging features is the ability to jump to a pointer or to read from memory. You can't single step, but at the same time, it has a password protection mechanism that's independent of the JTAG fuse protection. So if you blow the JTAG fuse, you can still access the chip through its serial port. Further, this is code within memory. It's always from C100 to 1000 hex. You can dump it, you can debug it, you can disassemble it, you can analyze it, and it has bugs. It's only 500 words long, but even at that length, it still has bugs. So there are the different commands that you can use with it. You can receive data, and that means that you're telling the board to receive, the victim to receive data. You can tell it to receive a password, you can erase memory, you can erase all of memory, you can see whether or not memory has been erased, and all of these things. But only the ones in the right column can be accessed without a password. And some, like the change baud command, now require a password in more modern versions. And the reason for this is that if you could tell it to transmit data to you, then you could just have it transmit the password. Or you could dump a copy of the firmware of the chip and then start making counterfeit boards. So commercially, if one firm got a board that belonged to a competitor, instead of spending the time to design it from scratch, they can just photographically copy the PCB layout. And then, if not for the protection mechanisms, they could also copy out the firmware, load that firmware into the new board, and sell it as if it were their own. And by changing the board layout and keeping only the firmware the same, it can become difficult to prove that your competitor has stolen your firmware. Also worth mentioning is that the change baud rate command doesn't actually change the baud rate. It actually changes the clock rate. We'll get into how it figures out serial timing, but in some versions you can change the baud rate to something very high, actually setting the clock very high, and then you can brute force passwords faster. Conveniently, those are the ones that my timing attack does not work against. So this was my first attempt at a cracking device. All through-hole parts, a very low-powered MSP430 in the middle. And with this device, I verified the behavior, but I never actually broke a board. The following version, shown here, uses surface mount components. This one is shown partially soldered. And this was the first to actually extract a password from a board. Since then, I've manufactured the BSL-C30, which adds voltage glitching and a third button. The fourth one will have 2 serial ports and some other enhancements. Now, to start the BSL, because keep in mind this is a microcontroller, it has no innate operating system. Usually you turn the microcontroller on by raising the reset pin from 0 to 1. And if your test pin remains grounded throughout that, then the user program will begin. If you send 2 pulses, and sometimes this is backward on another pin, if you send 2 pulses and the second pulse falls just after the reset line goes high, then instead of pushing the reset vector into the program counter, it pushes a vector found within permanent masked ROM. So usually the chip will look at 0xFFFE, take those 16 bits and push them into the program counter. By doing it this way, it instead looks at 0x0C02. And then on different chips, you do different lines. Now, so looking at a scope, you can see the timing. And once you initialize it, it's waiting for 0x80 to be sent across, because it needs to figure out the timing with which it's going to speak. And then you can view the conversation as bytes going across the wire between the 2 chips. And I'm going to refer to bytes as packets, because that's sort of how things work. Each one begins on a falling edge. After the falling edge, you've got your data bits, and then you have a single even parity bit to make the number of ones even. And then you have a stop bit, which is always high. When you do this and you give it the password comparison command, it runs through code that might look like this. And this is the invulnerable version. There's a comparison above the top. It comes down into the conditional jump instruction. This either goes left or right. If it goes left, you see a NOP instruction and a jump. Neither of these does anything except make sure that it gets to the end and that it does it at the same time as it would take if it went the right route. On the right route, it runs a bit immediate set, which disables access to the password-protected regions. Following this, there's a jump, again, keeping the timing balanced. So then at the end, 6 clock cycles have passed, whichever direction you went. Other versions look like this. You have a conditional jump, which goes straight to the end of the comparison. And then you have a bit immediate set. And if the bit is set, if that byte of the password is wrong, it takes 4 clock cycles instead of 2. So you have a difference of 2 in your comparison. And this code is run once for each byte of the password. So the password is 32 bytes, 256 bits. This code executes 32 times. So I loaded this into a simulator. I wrote a simple firmware image, which has a simple password. You just have an entry and then a for loop. The for loop calls the password comparison routine, and the idea is to run the routine for a guess of each of the 256 unique bytes. So we'll try all zeros, we'll try all ones, all twos, all threes, and then we compare the total runtimes. So in this case, 3 choices of bytes ran faster than the others. So 01, 02, 03, all of the bytes which don't exist in our password take 6,543 clock cycles. 00, 11, 3A, they all take less than that. And if we divide the difference in clock cycles by 2, then we see that there will be 1 instance of 00, 16 instances of 11 hex, and 15 instances of 3A. And sure enough, this is our password. And the password isn't chosen by the programmer. The password is the list of interrupt vector entry points. And there's a good reason for that too, because when you're making a product, you're just trying to ship it out the door. And in an ideal world, it would be different, but that's how the vast majority of engineering firms work. You don't have time to look into the security of each device. You don't have time to choose a good password. So in this case, by using the interrupt vector table, every complicated firmware image will automatically have its own sort of unique password. And the manufacturer will have a copy of that password, but no one else will. And the compiler can't not set the password. So when you have all of these fly-by-night, hey, let's make an MSP430 compiler companies, they all, by the very nature of the chip, have to make a unique password for each image. So to crack it, again, getting back to the timing, we need to stretch our timing for reasons that I'll explain in a bit. Specifically, if we send bytes which are the proper distance apart from one another, then the victim chip will wait for bytes. And so long as it's waiting for bytes, whatever timing variance might have existed has just been destroyed. Further, we need very low latency because we have to control exactly when the line falls, exactly when it rises. So the low latency is more than we can expect from a PC parallel port. And the solution is to use an MSP430 to attack an MSP430. So roughly we're looking at 2 microseconds per correct or incorrect byte. So we need to sample at least 1 megahertz. If there were a context switch in a PC, that would destroy this information and we wouldn't find the solution. So quickly reviewing RS-232, it consists of marks, which are zeros, and spaces, which are ones. There's a start bit to indicate the beginning of a byte, and a stop bit to indicate the end of the byte. And in this case, we have a parity bit. So if you remember from your BBS days, when you would connect it to 8N1, that means 8 bits, no parity, 1 stop bit. And then 1 start bit is implied. So in this case, we're on 8E1, which is different from the BBS days, but there's a good reason for it. So each packet begins with a single start bit, then the least significant bit comes first. You work your way up to the most significant bit, and then you have a single even parity bit followed by a stop bit. So considering the example of 0x80, it begins by a fall to a mark. The mark lasts 1 space, and then we have spaces for the individual data. So this would be our least significant bit, which is a 0. Then we have another 0, another 0, and another 0. This is our least significant nibble. Following that, we have the 3 zeros of the more significant nibble. Following this, we have a 1. That's the 1 within the 8. Following that, we have another 1 to make the number of 1s within the message even. And then we have a single stop bit. Now, 0x80 is sent before any given command frame to the bootstrap loader. Do any of you know why? For what?
Make it wake up?
Not quite. This is how it determines how quickly the transmission will be. The message looked, think of it as a difference between the 2 edges. If you divide that by 8, you get the width of 1 bit. So that's what it does. It tars its own time by measuring the difference between these 2 edges. And that's how it knows how quickly to speak to you. As long as you don't overrun or underrun this counter, you can choose any odd baud rate that you like. If you speak to it at 9600 baud, it works fine. 9605 works fine. 9700 works fine. And because of this, you can make it speak more quickly or more slowly than it's supposed to. To send 0x90, again, we have the less significant bits, followed by the 1. And then we have the most significant bit. That's the 8th bit in the 9 nibble. But here the parity bit is 0. If you look at these enough, it's easy to recognize the difference in a scope recording. Now, this is implemented, and I believe I screwed up this slide, but the gist is that you have an input pin, and you have a while loop watch to make sure that it's always high. And it just sits there spinning until it drops low, at which point it checks to make sure that it's low, and then it shifts in the bits and everything and checks the parity. But it will, if you already have it low by the time that it enters this, then it just falls through. It never waits on you. Now, samples are only taken at discrete points. So it just looks at the pin. Let me grab some water. So it checks it only at one moment in time, and it bases all of this timing on that single falling edge, which might not actually be a falling edge. If you make it already low and you guess at the moment at which it will start, then you can be sure not to knock its timing off, but at the same time, you can sort of guess at its timing. And by speaking slowly, by sending your bytes slowly, you're able to send lots of bytes, have little error in interpretation, and at the same time not affect timing. So the conversation will look like this. You have a SYN message from the attacker. That's 0x80. The victim will acknowledge with 0x90. Then you'll have the packets of the attack frame. This begins with a header, a command byte, then you've got lengths, you've got 4 bytes that don't matter, and after the LH is when your password begins. And you have to begin doing your weird timing with the password. You don't have to worry about the header byte or the command byte resetting timing because nothing has occurred that's worth measuring yet. So if you think of this as a race, after you send the 4 bytes that don't matter, the AL, AH, LL, LH, then the line is high, and when you drop it low to begin sending your password, that's when the starter pistol fires. That's when you have to begin measuring timing. In RS-232, it begins listening at some point. Then with the bit-banged implementation, you see it waits for the falling edge, and then it measures everything after that. Ideally, we would like these to line up perfectly. Instead, we drop it low early, and then we predict when it will begin listening. And then you can avoid these errors. You can avoid affecting its timing, but at the same time, you can measure the result. Some other fun stuff that you can do. You can drop the voltage to the victim chip beneath the documented minimum voltage just for a bit, and then bring it right back up. And if you're lucky, on any given attempt, you do lots of attempts to get this to work, you can mis-execute or skip instructions. This is a commercial device, semi-commercial, for doing that to smart cards. Satellite TV pirates use this to re-enable a smart card that's been disabled. And basically, you've just got this mux. We've got 1 voltage, then a fraction of that voltage. You drop the mux, bring it right back up. On a scope, it looks sort of like this. This is my first attempt at building one of these things. This is my business card with an LED on it and a resistor, and it runs a program that's just an infinite while loop, and then after that there's an infinite blinking loop, and the second loop should never run. But in this layout I had a modified BSL cracker, and then I've got a voltage glitcher, and I've got my business card. And by triggering the glitch, I can make the business card skip into the section of its code that starts blinking that LED. Now, it's not terribly useful if all you can do is light an LED, but if you look at the way that the BSL is disabled, you put the constant AA55 into memory at FFBE. It's part of flash memory. And when it starts up, early on in the BSL, it checks them. And if the two are equal, if the constant AA55 and then the contents of memory at the BSL key address, it enters an infinite while loop, the JZ plus 0 in assembly language. And the single instruction just keeps jumping to itself. But if you can skip that one instruction, then it falls through to the next instruction, which is where it would be if the programmer had intended the BSL to be active. So in doing that, you can break into a BSL that has been disabled. If I know the password, but you've turned off the BSL, I can still get into it. Another issue is that it's difficult to time the glitching if you don't know exactly when the clock pulse will hit. And the clock is only exposed if you choose to expose it. The external crystal is at 32 kilohertz, and then a PLL multiplies that frequency for the internal clock. And even then, the external crystal needn't be used. It's not powered up when the BSL is running. So instead of sharing the crystal between two or doing weird stuff like that, you can do power analysis on the board. Okay, so in this case, we're trying to find the instant in time at which a clock edge strikes. And here are some clock edges coming out of the VCC pin of the chip. If you remove the bypass capacitor, the chip still functions. But whenever a clock edge hits, that's when the chip is doing actual calculations, the voltage falls. And there's not much that they can do. There's not much that they can do about this because it's a power-efficient chip. You buy this because you want it to run on a battery until the end of time. And if they were to make it use this much power at all times, then you wouldn't get that advantage from the product. So I'm presently working on a device which extracts this clock and just gives you a digital square wave. And then you can time your glitching on that square wave. So back to the BSL cracker. I started with the first generation model, then the second generation, and now the third. I apologize for being in black and white. The only picture I had on my laptop was from the paper, which you'll find in the proceedings. These two chips on the right are both 4053 muxes, which can be used to do a voltage glitching attack on the device that you're communicating with. And at this point, all of the I/O lines are switched to high impedance so that no power can be sucked out of them. And then the voltage line drops to a lower voltage that's controlled by an I/O pin. By use of this, you can glitch past a disabled BSL. With better firmware, you should be able to glitch past the password comparison itself. If you glitch through it such that it never actually compares a byte, then it can never disable your access. And the way the code works, it first gives you access, and then it compares all of the bytes. And if any byte is wrong, it cuts out access. If 12 are right, it cuts out access 12 times. But if none of them are compared, then it never cuts out access. If only the first one is compared, then you only have to get the first one right. And this is in a loop, so falling out of the loop allows you to skip all of the rest of them without having to perform the glitch multiple times. So are there any questions?
Yeah, please use the microphone for the benefit of those who cannot be among us.
Cheers. Did you have access to the BSL source code before you started doing these attacks?
No, and I still don't have access to it. But if you'd like to play with this, In the appendix of the paper that you'll find in the proceedings, I included a list of the functions that I've identified within the BSL. Most of them are actually subroutines, because it's part of some grand switch statement. But there are also a few functions, and then interesting regions of code, global symbols, and a table of those going from English names to hexadecimal addresses is included. So I printed out the disassembly of the code. And then for a couple of days I went through and I annotated the different pieces of it. The lecture that I'll be giving on the 29th in Sal 2 on repurposing the EZ430 describes the tools that I used for this. I've got a Perl script called MSP430 static that lets me say identify every function that contains access or code that writes to a particular I/O port. Okay, so in the BSL code there's a read byte function and a write byte function. And then there's a tare function that reads the 0x80 and bases a timing guess upon that. And the program is only 500 words long, 1 kilobyte. That's a hard limit by the architecture. So it's feasible for a human being to go through and to learn it all. Any others?
Thanks.
Oh, yes.
More questions? Comments? Well, if you are happy right now, I have a somewhat non-technical question. Now, you have the DMCA in the US, which probably forbids what you're doing. Do you give that stuff any thought?
Well, I mean, the DMCA is intended for media mostly, so I decided to go by the spirit of the law, I suppose.
So you don't worry that TI will send lawyers to you?
Well, I haven't found many devices which do have the JTAG fuse cut. Most devices actually leave it open. And it makes sense from a manufacturing standpoint, because if you mess up a manufacturing run and you need to fix things, the JTAG fuse is just in the way. Yeah, so.
Any look?
Do you know of any other microcontrollers where such attacks have been already done, or like the AVR, or?
Yes, the voltage glitching technique is actually rather standard for smart cards.
Okay.
As far as the timing attacks go, I haven't been able to find published prior art, but I have been able to hear that others have done it before me from casual conversation.
Okay, thanks.
So, whenever you do a password comparison on a microcontroller, realize that the device that you're speaking to can observe everything about how long it takes you to compute the password. TI's latest defense against this is to erase all of flash memory the first time the password is wrong. And on those versions, while the timing vulnerability exists, it's not terribly useful unless this booby trap is disabled. Yes?
How long did you say the timing glitch on the voltage rail had to be?
I've had luck with about 45 nanoseconds.
Oh, and you managed to generate that with the muxes and an MSP430. What speed's the MSP430 running at?
If I jump back to the picture, no, that's not it. I'm not sure how much of this is affected by the capacitance of my probe, but you'll see that it's not a very square drop.
So I was wondering if you could do it just with a cap from an I/O pin on the MSP430 going into the rail, just have a falling edge on the other side of the cap.
You can. In this case, I used the muxes so that I could switch to a particular voltage. So I can add a capacitor to a test point on my board, get the capacitor at the value that I want to glitch with, and then flip everything over. Yes.
I have one general question. I'm not that familiar with that type of microcontroller. In what type of devices is this normally used?
This is used in low-power medical devices. One of the more popular application notes is a pulse oximeter. Also, it's used in Zigbee, wireless sensor networking. TI just announced the CC430, which is an 802.15.4 wireless radio and an MSP430 within the same package. It's used in multimeters, in altimeters. I'm sure someone's built a wristwatch with it. So.
Okay, so if there are no further questions, last chance. Right.
You mentioned software simulator. Can you get a little bit more in details which you have done there?
The simulation of the exploit, or the simulation of the timing?
It's the timing simulation. Had you built a program which rebuilt the MCU with respect to fill in the bytecode, or had you some other way to...
There is a publicly available simulator written in Python that ships with the GCC port to this architecture. There are also some simulators written in Java and C++ that I haven't had time to evaluate.
Okay, so programs of 500 machine words. I get young again. So let's thank Trevor for that wonderful talk, and see you.